So in the second part of my lecture of fault analysis, I'll discuss the topic the fault current calculation by using the impedance matrix. So the fault can be occurred of interconnected power system. The power system which consists number of generators or motors or different types of buses are connected together. So in this interconnected power system, there can be a short circuit fault maybe occurred here. So if a fault is occurred in an interconnected power system, we can calculate the short circuit fault current by using the impedance matrix. So at first, we have to derive the equation, that is how we can calculate the short circuit current by using this impedance matrix. So to discuss this topic, here there is a online diagram of a particular power system. This particular power system contains 4 buses, and bus number 1 is connected with a generator, and this J.12 is the subtransient reactance of the generator, and this is the reactance of the transformer T1. Similarly, the motor is connected to bus 3, and this is the subtransient reactance of motor, and this is the subtransient reactance of the transformer T2. Now, the line reactances are given in this diagram. From this reactance diagram, we can easily draw a admittance diagram, and this is a susceptance or admittance diagram. So we can easily, well, this is also impedance diagram actually. This is the admittance diagram. So we can easily calculate this admittance diagram from the impedance diagram. Now, previous 2 slides, there are 2 different symbols added in this impedance diagram. Number 1, we have assumed a 3-phase short circuit fault occurred at bus 2. So we have assumed a 3-phase short circuit fault occurred at bus 2. So whenever a short circuit fault occurred at bus 2, it means that a short circuit current flowing from bus 2 to the neutral. So this short circuit current we here denotes by IF double prime. This is the subtransient short circuit current. And without a source, there will be no current flowing to the any path. So that's why the fault voltage is the VF, and fault voltage is mainly the bus voltage at bus 2, because the fault is occurred at bus 2. So this is the bus 2 voltage is denoted as VF, that is the fault voltage, and here this symbol is determined, or this symbol is given to understand this is a voltage source connecting to the bus to the neutral. So this the short circuit current is flowing through the path. Now, after the short circuit fault, we know the voltage of a short circuit bus is 0. So to identify this thing, here a opposite voltage source is add with series to the existing voltage source. It means that plus VF plus minus VF is equal to 0 volt. So that is the voltage source should be eliminated and the short circuit branch voltage should be 0. To represent this thing, here two opposite voltage source connected in series. So now this is the admittance diagram, which we can easily draw from the impedance diagram, and based on this admittance diagram, this is the Y bus matrix or bus admittance matrix for this particular power system. Now we know for a interconnected power system, the current equation I is equal to Y bus matrix into bus voltage V. So this is a 4-bus power system. That's why the dimension of Y bus matrix should be 4 by 4. So the element should be Y11 to Y44. This is the 16 element of this bus admittance matrix. Now, this is the node voltage or bus voltage. So there are 4 buses. So there should be 4 bus voltage. That is the V1, V2, V3, and V4. Now, when the fault is occurred, that time the bus 2 voltage should be equal to the fault voltage, that is the minus Vf. So that's why bus 2 voltage is replaced by the fault voltage, that is the minus Vf. And next, bus 1, 3 and bus 4. So whenever the fault is occurred, that time the bus voltage should be changed. So this change is represented by this delta. So that is delta V1. It means that the change of bus voltage 1. That is delta V3 and delta V4. It represents the change of bus voltage V3 and V4. That the change of bus voltage 3 and 4. Now, whenever a short circuit occurred, that time the current is following only through the short circuit path. Other branches current should be 0. So that's why bus 1, bus 3 and bus 4 current is 0. Only the bus 2 current, that is the short circuit current minus our double prime, is exist here. So now if we want to calculate the bus voltage change at the instant of initiating fault, then this bus voltage change should be in the left side of the equation, all other things in the right side of the equation. So whenever we want to shift the admittance matrix to the right side, this admittance matrix should be inverse. So the inverse of admittance matrix is called the impedance matrix. So what is the impedance matrix actually, or the Z-bus matrix? So the impedance matrix means that the inverse of Y-bus matrix. So you have to identify the system Y-bus matrix first. Next, whenever you invert this matrix, you will get the impedance matrix. So from this equation, we can easily find out the individual equation of bus voltage change at the instant of initiating fault. So that's why if we consider the del V1, that should be Z12 minus IF double prime. So these are the equations. So from this, we can easily calculate the short circuit current IF double prime, that is short circuit voltage divided by self impedance of the short circuit bus, that is Vf divided by Z22, self impedance of the short circuit bus. Now, so the voltage differences at each node due to the fault current can be calculated. So this is the voltage change of each bus at the instant of initiating fault, that is del V1. We can put down the short circuit current value here. So the equation should be minus Z12 by Z22 into fault voltage, and the rest are the follows at the same path. So after occurring the fault, what is the new bus voltage? So if we want to calculate the new bus voltage after occurring the fault, that is the V1, V2, V3 and V4, then we have to add this bus voltage change with the pre-fault bus voltage. So before occurring the fault, the bus voltage, or what is the bus voltage? We have to add this bus voltage with the bus voltage change at the instant of initiating fault. So that's why this is the pre-fault voltage, and plus this is the change of bus voltage at the instant of initiating fault. And if we add these two value, we will find out the bus voltage after occurring the fault. So this is a flat assumption, that is the pre-fault bus voltage is equal to the fault bus voltage or fault voltage. So this is a flat assumption. So if we assume that the pre-fault voltage is equal to the fault voltage, then this is the pre-fault voltage equation, that is equal to the fault voltage, and we can put the equations of bus voltage change here. Then we can easily take the common of Vf. Then these are the final equation, and here the fault is occurred at bus 2. That's why the bus voltage at bus 2 is equal to 0. So we can formulate a general equation. So any short circuit current we can calculate by using this impedance matrix for an interconnected power system. A simple general equation is the short circuit fault current is equal to fault voltage divided by self impedance of the bus in which bus short circuit fault is occurred. It means that if a 10 bus power system short circuit fault is occurred at bus 5, then the short circuit current should be equal to fault voltage divided by self impedance of bus 5, that is Z55. Now, after occurring the fault, the bus voltage change should be, or the new bus voltage we can find by the equation of Vj. This is the general equation. J is the bus number for which bus we want to calculate the voltage is equal to 1 minus Z Ji divided by Zii into Vf. So here, if there are 10 bus, this is a 10 bus power system and fault is occurred at bus 5, and we want to calculate the after fault voltage at bus 3, then J is equal to 3. So V3 is equal to 1 minus J ZJI. So I means fault bus number, that is 5. J is the bus voltage, that is 3. So Z35 divided by ZII means Z55 into fault voltage. So this is the general equation. And finally, if we want to calculate the branch current like this, if we want to calculate the current following from bus 1 to bus 2, this is a branch current, then the equation should be after occurring a fault. So the equation should be bus voltage V1 minus bus voltage V2 into the branch admittance. So the branch admittance is here minus J5. So into the branch admittance. Like this, if we want to calculate the current following from bus 3 to bus 2, then the equation should be V3 minus V2. So the voltage difference from bus 3 to bus 2, V3 minus V2 into the branch admittance, that is minus J5. So this is the equation, a line current flowing equation. So that's all about the theory. Now we can solve this mathematical problem very easily. So here, this is the 4 bus power system, and here a short circuit fault is occurred at bus 2. At first, we have to calculate the per unit short circuit fault current, that is the subtransient fault current at bus 2. So to calculate the subtransient fault current, at first we have to calculate the bus impedance matrix. So this is the admittance matrix of the system, and this is the impedance matrix of the system. And this impedance matrix is the inverse of bus admittance matrix, not the inverse of element of bus admittance matrix. This impedance matrix is the total inverse of Y bus matrix. So the per unit subtransient fault current I can calculate, that is the, for a given power system, we know the fault voltage is 1 angle 0 degree per unit, because here there is nothing mentioned in the question about the rating of the machine or about the fault voltage. So if in the question there is nothing mentioned about the fault voltage or the rating, we can assume the fault voltage 1 angle 0 degree per unit. So here we can assume the fault voltage and pre-fault voltage at the machine base value at the rating 1 angle 0 degree per unit. So the short circuit current should be Vf divided by the self impedance of the fault bus. So Vf divided by Z22. So we can easily calculate the short circuit current. Next, question number 2, calculate the per unit voltage at every bus in the system during the subtransient period. So you have to calculate the bus voltage during the subtransient period. So bus voltage. So here we can easily know the equation, that is 1 minus Z12 by Z22 into Vf for the bus voltage equation of V1. So here Vf is 1 angle 0 degree, and the impedance element of impedance matrix we have already identified. So you can easily calculate the post fault bus voltage. And here one thing, that is the bus voltage at bus 2 is 0, because at the instant of initiating fault the short circuit bus voltage should be 0. And finally, calculate the per unit current I1 flowing in the line during the subtransient period. So there should be current flowing I1 from bus 1 to bus 2. So here the equation should be V1 minus V2 into the branch admittance. So this is the equation, V1 minus V2 into the branch admittance. So there should be a minus actually in this here. There is plus, but there will be a minus. So the angle should be minus 90 degree. So this is the answer actually. So now our next topic, I am going to discuss the next topic, that is the unsymmetrical fault. So that's all about the symmetrical fault. So in symmetrical fault, we'll discuss the symmetrical fault. If a symmetrical fault occur in unloaded generator condition, what will be the process of calculation or procedure of calculation? If there will be a load connected to the machine, what will be the procedure of the calculation? And if interconnected power system, and there will be a symmetrical C-phase short circuit fault, what will be the procedure of calculation? We have all discussed here. Now the new topic under this fault analysis is the unsymmetrical fault, and the first part of this unsymmetrical fault is symmetrical components. So we have to know what is the symmetrical component actually. So symmetrical component is a technique to solve the unbalanced power system vector. We know if a unsymmetrical fault is occurred in a power system, then the vectors are not in a balanced condition. They are in imbalanced condition. So to calculate the imbalanced vector, there will be a technique, and this technique is invented by the Fortescue in 1918. So this is the symmetrical component method, and this method is being used to analyze the unbalanced system current calculation or voltage calculation. So if we consider as figure 1, this is the original system vector. That is the VA is the red one, VC, this is the green one, and VB, this is the blue one. So the anticlockwise direction, this is the ACB phase sequence. And if we consider this is the original phase system phase sequence, and this magnitude of all vector should be equal, and the angle displacement between them are 120 degrees. So this is the original system diagram. If we consider a power system which vector diagram is look like this, then this is a balanced system original system diagram. Now, if there will be a unsymmetrical fault is occurred in this power system, then the power system's vector are not being balanced. So these will be the unbalanced and maybe look like this. So this is a vector. This is the VA1, VA actually, this is the A phase voltage, and this is the VB, B phase voltage, and this is the VC, that is the C phase voltage. And the angular displacement between them is not 120 degree now, and their magnitude are not same also here. So this is an unbalanced condition occurred whenever an unsymmetrical fault occur in a power system. To balance this power system, we have to introduce the symmetrical component. Symmetrical components are the balance component, which we have used to balance the unsymmetrical vector of a power system or an unbalanced vector of a power system. So there are three types of symmetrical component. Number one, positive sequence symmetrical component. Number two, negative sequence symmetrical component. Number three is the zero sequence symmetrical component. So the positive sequence symmetrical component is similar as the system symmetric system component. So these are denoted at suffix 1, that is VA1, VB1, VC1 for voltage, and for current I1, IB1, IC1. So these are the positive sequence symmetrical component. The angular displacement between them are 120 degree, and the magnitude are same, and the phase sequence is same as the original system. Now the negative sequence symmetrical component, so the magnitude of all vectors are similar, phase displacement is 120 degree, but the phase sequence will be opposite as compared to the positive sequence original system. So if the original system phase sequence is ACB, here the negative sequence symmetrical component, the anticlockwise phase sequence should be ABC, and it's denoted by suffix 2. And finally, the zero sequence symmetrical component, their magnitude are same, but their angular displacement is 0 degree. Means that they all are the same value. So they all represent the same value. So we denote it by 0, that is VA naught, VB naught, VC naught actually for voltage, and for current I naught, IB naught, IC naught. So these are the symmetrical components. So these are the three symmetrical components we have introduced to solve our unbalanced vector to calculate the short circuit current or voltage. So here every symmetrical component have, for each phase, if we want to balance the yes, for here, if we want to balance the unbalanced system, we have to introduce total 9 symmetrical components. For each phase, there should be 3 symmetrical components. Like if we want to replace this phase voltage VA or unbalanced system voltage, we have to replace it by 3 symmetrical components. At first, VA1, that is the positive sequence symmetrical component, plus VB2, that is the negative sequence symmetrical component, plus VB0, that is the zero sequence symmetrical component for phase A. Similarly, for phase B and phase C, we have to introduce these 3 symmetrical components for every phase voltage or current to convert the phase unbalanced voltage or phase unbalanced current to the balanced condition. Well, so now if we want to know the equation of symmetrical component of voltage or current, how we can calculate the equation of symmetrical component. So we have to use the A operator. So this is a one angle 120 degree operator, and A square means one angle 240 degree. So we can use this to replace the displacement from one phase to another. So now we know that is the phase voltage VA means VA naught plus VA1 plus VA2. Three symmetrical component. If we add this three component, we can find out the phase A voltage. Similarly, for phase B, we can add VB naught, VB1, and VB2. And for C, we can write down VC naught, VC1, VC2. But we can easily replace this VB naught, VB1, and VB2 by VA naught, VA1, and VA2. And similarly for phase C, how we can convert this. So here VB1 is equal to what? VB1 is present and VA1 is here. So the displacement, the anticlockwise displacement from VA1 to VB1 is 120 plus 120. It means that 240 degree. So 240 degree means A square. So if we multiply A square with VA1, we can easily find out the VB1. So we can write down VB1 is equal to A square into VA1. Similarly, for VB2, the displacement from VA2 to VB2 is A, that is 120 degree. So if we multiply A with VA2, we can easily find out the VB2. And VA0 and VB0 are same, so you can easily write down the VA0 instead of VB0. Similarly, the VC1, the displacement of VC1 to VA1 is 120 degree from A to C, anti-clockwise direction. So we can multiply VA1 with A to find out the VC1. And similarly, rest of two. So we can easily convert our equation B0, VB1, and VB2 by VA0, VA1, and VA2. Similarly for C phase. So here there are three equations. We can easily write down this in a matrix form. So this is the phase voltage, this is the symmetrical component of voltage, and this is the A matrix or constant matrix. So phase voltage is equal to A matrix into symmetrical component of voltage. So now if we find out the symmetrical component of voltage equation, we have to shift this A matrix from right to left. It means A inverse. So this is the A inverse matrix. So finally, we can find out the equation of symmetrical component of voltage in terms of the phase component. if we want to find out the current equation of symmetrical component, then the process is all same and the equation should be same, just the notation will be different. That is, the notation V that stand for voltage will be shifted as I that stand for current, nothing else. So there are some simple mathematical problem like this. This is the theoretical problem actually at first. That is the proof that the neutral current of three-phase alternator is equal to the 3 times of its zero sequence current component. So this is a theoretical problem. So we can easily prove it by the help of the symmetrical component calculation. So we can easily find out the symmetrical component of current equation, and from here we know the zero sequence current is equal to 1/3 of IA plus IB plus IC, and if it is a Y connected machine, then the sum of these three phase current should be followed by the neutral. It means that I naught is equal to 1/3 of IN. So neutral current should be 3 times of zero sequence current component. So this is the proof actually. So this is the answer. That is, the neutral current should be 3 times of zero sequence current component. And for this type of derivation, we have to draw this figure actually. These three figures, we have to draw this. For current, this notation should be I, and for voltage, that notation should be in V. Well, so now these are the small math. Like first, the line currents are given. We have to find out the symmetrical current component easily. If we put this value in this equation, we'll get the answer. And if the symmetrical component of voltage are given and we have to find out the phase voltage, easily we can find out this by put this value in this equation. So these are the some simple math. And now this is a derivation. This is a theoretical derivation. So we know the complex power equation, that is P plus JQ, is equal to voltage into current conjugate. So if this power equation we can write for three-phase system, then this should be VA into IA conjugate plus VB into IB conjugate plus VC into IC conjugate. This is the three-phase power equation. Obviously, this is a three-phase complex power equation. Now our topic is power in terms of symmetrical components. So we want to replace this power equation by the symmetrical components. So how we can do this? So this is a complex power equation, voltage into current conjugate. Now we can shift this row vector to column vector. It means that the transpose of this voltage matrix. So here, if we want to replace this phase voltage by the symmetrical voltage, then we can write this by A into symmetrical component of voltage, because here phase voltage is equal to A matrix into symmetrical component of voltage. So A into symmetrical component of voltage. Like similarly, phase current should be A matrix into symmetrical component of current. So here we can just break down this equation and put this value. This is the symmetrical component of voltage. This is the A matrix, that is the transpose, and this is the A conjugate. This is the A matrix. We have to conjugate this, and this is the symmetrical component of current, obviously the conjugate. So if we again transpose this column to row vector, then this is the row vector. This is the A transpose matrix. This is the conjugate matrix, and this is the symmetrical current component conjugate. So we have to multiply this A matrix with this A conjugate. We will find out 3, and this is the symmetrical component of voltage, and this is the current. So if we multiply this, we will find out that the complex power equation in terms of symmetrical component should be 3 into VA naught I naught conjugate plus VA1 I1 conjugate plus VA2 I2 conjugate. This 3 is multiplied with the whole equation. So this is the derivation actually, and this is the derivation of complex power in terms of symmetrical component. So this is the second part of photo analysis lecture. My third part, I will discuss about the sequence network. So that's all for today's lecture.